ahead and start the recording of the session and minimize mine and get it out of the way. And this is the way it works. Anything I write here, you should be able to see. You see what I'm writing?
Mm-hmm.
Okay. And we just pretty much proceed like that. Now, do you have any specific problems you'd like to go over today that you might be able to verbalize, like if you want to practice factoring or completing the square or things like that?
Whatever you think would be best. All of the programs before school are just to help me get back in the mind space of being in school.
Okay.
So whatever you think would help me the most.
Let's do some factoring. You can never get too much practice factoring. And
I agree.
It's definitely something that you're going to have to do tons and tons of. So let me put up a couple of problems. Yeah, let's start with this. Factor that expression. What's the greatest common factor?
2.
It's actually 2x. In other words, when I'm looking for a greatest common factor, I'm looking for the greatest thing that will divide into both expressions. And not just 2, but x will also. So if I take out a 2x, what am I left with?
Take out a 2x, you're left with 3x. For
X minus 3. In other words, when I say take out a 2x, what you're basically doing is dividing each term by 2x. Okay? And whatever the result of that is, goes here. Whatever the result of that is, goes here.
So it isn't 3x that's left? I mean, you divide the 2x away and then suddenly there's no more x?
Right, exactly. And I can prove it by multiplying these two things back together again. In other words, if I distribute the 2x to this expression, I get 2x squared minus 6x. That's always the proof of the pudding when you're factoring, is after you have factored it, make sure that when you multiply it back together again, you get what you started with. If you don't, you've done it wrong, and it's as simple as that. Okay? Now, why would we want to factor this? Let's say we started with an equation where that whole thing was equal to 0. Well, I can't solve that because I've got two things being subtracted from one another that are equal to 0. So the whole reason that I factor it is so that I'll end up with the product of two things. I want two things that are multiplied together equaling 0. Because once I get that, now the rules of algebra says that you can't multiply two things together and get 0 unless one of them is 0. So the next step is to set that equal to 0 and to set that equal to 0. Well, if I set 2x equals 0, well then one solution is x equals 0. And if I set x minus 3 equal to 0, then the other solution is x equal 3. And those are my two solutions if I started out with an equation. But it illustrates why we need to factor so much. Is because we're always trying to take stuff that's being added and subtracted and turn it into two things that are being multiplied. Okay? So there are basically 4 or 5 types of factoring. One is what we just did, greatest common factor. Okay? The next factoring is where you just take this, and let me put up that example, just so we'll know. In other words, we didn't do anything special there other than find the greatest common factor. there's another one called difference of perfect squares. Which I call dopes. How does that factor?
X minus 9 and x plus 9.
It's always the square root of that minus the square root of that. So it's x minus 3, and then the right side is always the conjugate, x plus 3. Okay?
Okay.
So what is factor that using difference of perfect squares? What's the square root of 4x squared?
2x.
2x, okay. First one, always minus. The second one, always plus. Doesn't seem like it should make a difference, but when you get to... Have you covered sum of cubes and difference of cubes before?
Some, I don't think much.
Well, when you go to memorize those, it's very helpful if the sign on the first term is the same as the sign on the expression. So that's why I like to make the first term negative and the second term positive. I realize you could reverse them if you wanted. But I try to get my students to memorize it this way because it'll make it easier to memorize when you get to the difference of cubes and the sum of cubes. So what goes here?
They're 3y.
Okay. And then over here?
2x plus 3y.
That's it. Okay, so difference of perfect squares is pretty easy. And in actuality, it doesn't actually have to be perfect squares. If I wanted to factor that, that's not the difference of perfect squares, but I know it factors into the square root of x minus the square root of 7 times the square root of x plus the square root of 7. So they call it difference of perfect squares only in the beginning of algebra. It actually works with any expression. It's called difference of perfect squares because it kind of originates from, this is the way they teach it. There's the difference of perfect squares. That's a perfect square, that's a perfect square. They're being subtracted. And that always goes to a minus b times a plus b. Okay? Now, the one that a lot of people don't recognize when they're looking at it is this one. How's that factor?
It would be x minus 1 and the next one would be x plus 1.
Yeah, 1 is a perfect square. So I can apply it because that's a perfect square. Okay, so that's greatest common factor, difference of perfect squares. Before we get to the third most common type of factoring, which is where you're factoring a quadratic that has a constant in it, there's one other kind of thing that goes along with that. How do I solve that?
That is, you just take the square of each one and x equals 5.
You take the square root of each one, but there's a catch here. When you take the square root to solve an equation, your answer always should start out plus or minus. That's the answer. It's plus or minus 5. Notice that minus 5 works just fine. Minus 5 squared is 25. Okay?
Mm-hmm.
The other way we could do this, it's actually harder, but it ensures you don't make a mistake, would be let's subtract 25 from both sides. And now we really do have difference of perfect squares, which factors into x minus 5 times x plus 5 equaling 0. And now you can see that your solutions are 5 and minus 5.
Yeah, I like that.
So it actually, this saves you from making the mistake that I will say 90% of students make. 90% of students are going to tell you 5 there. They're not going to tell you plus or minus 5. I cannot figure out a way to get students to remember that. You know, I wish I had a song like the song they teach you to remember the quadratic formula. You know, whenever you're solving an equation, by taking the square root of both sides, begin your answer with plus or minus. It's the way my song would go.
Lovely.
Something like that, with tune. Okay, so those are 3 basic methods of factoring. Now let's talk about something that looks like this. It's their greatest common factor.
It's 1. 1x.
Well,
No.
it's not x. You can't divide this third term by x.
No, there's no
So
x.
there's no x that can be brought out. And you're right, 1, but we don't consider 1. When we're looking for greatest common factors, we're only looking for things greater than 1. So there is none. So we can't use a greatest common factor. If I've got this whole thing equaling to 0, I got to figure out a different way to factor it. It's not difference of perfect squares. I can't factor it like that. So what I basically have to do is unmultiply that. In other words, this quadratic was produced by multiplying 2 linear terms and foiling them, right? So all factoring is doing is separating this out into the 2 linear terms that produced it. Have they taught you something called the California method or the diamond method?
They've mentioned it. Yeah, I think they did.
Okay. I don't like either one of those. I like my method. So you may end up in class having to show your work and show how to do it using one of those methods, but I'm going to show you a much easier way to factor. Particularly when you're dealing with what I call level 1 quadratics. A level 1 quadratic being the x squared term does not have a coefficient. It's just x squared. These are particularly easy to factor. If I had a 2 there, it becomes significantly more difficult. It's more of a trial and error process. But as long as that's a 1, let's work with these for a little bit. There's 3 basic steps to factoring. The first step, separate your x squareds. The moment I've done that, in my mind, I am multiplying that back together again to make sure I get x squared. Okay?
Okay.
Always make sure when you split this apart that the 2 things multiply together to give you that. Second step, determine both signs. What are my signs going to have to be? For me to produce a plus 10, they have to be the same, right?
Yes.
So they have to either both be negative or both be positive. Otherwise, I never could have produced a plus 10. Well, to determine which, look to the sign of the middle term. It's plus. They have to both be plus. That's step 2. Step 3. Factors of the constant, 10, that add, because of that plus sign, to the number in front of the middle term. 7, not plus 7, just 7. Well, what factors of 10 add to 7?
2 and 5.
That's your answer. Easy enough. Let's change it slightly.
This is just a hard thing to get.
Let's put a negative 7x there. Now, first step, split apart the x's, it's still x and x. What are both signs?
Minus.
Minus, because minus times minus will give me the plus 10, and it's also going to give me a negative as a middle term. Now I'm looking for the same thing. I'm looking for factors of 10 that add to 7. So my answer is still that and that. Okay? So as long as this is a plus sign, these are relatively straightforward and simple. Let me just give you one more. First step.
Find common parts.
Split apart the x's squared.
Separate the squares.
For our level 1 quadratics, it's always x and x. Second step.
Determine both signs.
Which are?
And they're going to have to be both negatives. Minus.
Third step.
Third step is factors that add to 27, but add together to make 12, but multiply to make 27.
Yeah, there you go. Factors of 27 means two numbers that multiply to 27. So you can just think of it as factors of 27 that add to the number 12. Not the minus 12, just to the number 12. What are they?
3 and 9.
And it doesn't matter whether the 3 goes here and the 9 there or vice versa. Okay? So as long as that's a plus, these are quite easy. As long as this is a 1 and that's a plus, there's only 3 steps. And you've got these simple rules that apply. Okay? Now let's change it to a minus. The only difference now is there's going to be a fourth step. First step.
Okay. First step, split it apart.
So what should I write?
X minus.
Hold on. That's the first step.
Yeah.
Now the second step is to determine both signs. What do the signs have to be? Signs have to be subtraction. Opposite one another. They don't have to be subtraction, they have to be opposite. One has to be a plus, the other has to be a minus.
Is that because they're not equal to 0?
No, it's because remember what's going to happen here. I'm just going to go ahead and complete this. The next step is going to be factors of 27 that subtract to the number 6. Well, that would be 9 and 3. And now there is a fourth step, which is to take the largest of those factors and put it with the sign of the middle term. So I'm going to take the 9 and put it with the plus sign. So there's the fourth step, because you have to figure out which factor to put with which sign. So this is slightly harder, but the logic is still a bunch of rules that you can always state. In other words, the third step is factors of 27 that subtract to the number 6. And then the fourth step is put the larger of those factors with the sign of the middle term. Can
we go over this again slowly?
Yep, absolutely. We'll go over it as much as you want. This time I'm going to change that to a minus 6x. So let's go through all 4 steps. First step is that. Second step is the signs have to be opposite one another. One has to be plus, one has to be minus. Otherwise, I would never be able to produce that minus 27. You can't get a minus 27 if both signs are the same. You would automatically have a plus.
Got it.
So it's plus minus, and it doesn't matter whether I write plus minus that way or whether I write minus plus. It's going to be the same and for these problems. Okay? That's step 2. Step 3, verbalize it.
Step 3, find the parts that go
That's factors of
subtract
27.
to make 6, but multiply to make 27.
And subtract to 6.
Subtract to 6, yeah.
That's still 9 and 3. So those are my factors. And what's step 4?
Step 4, figuring out which one goes in which slot.
Okay, and what's the rule? The larger of the factor goes with which sign?
Plus?
The sign of the middle term. In this case, the sign of the middle term is negative. So my 9 goes there, my 3 goes there. Now, if my life depended on it, I would want to FOIL these back together again to make sure I got what I started with, right? Well,
yes.
FOIL these, term by term. What do you get?
All right. First, which is x times x, is x squared.
Okay, what's next?
First. Then it's the outside, which is x times 3, which is 3x. And then it's the inside, which is negative 9 times x, which is negative 9x, minus 9x.
And finally, the last
is 3 times 9, which 3 times negative 9, and that is negative 27.
Notice that the only way I was able to produce that negative 27 is if my signs were opposite on those two numbers.
Yeah.
So I'm basically working backwards. Now, once you've FOILed a linear term times a linear term, the only terms that can be combined are those middle two terms. And if I combine them, in other words, there's no other x squareds, there's no other numbers, but there is plus 3x and minus 9x. So if I combine those, voila, I get what I started with. That's the proof of the pudding, is that when you multiply everything back together again, you get what you started with. Well, let me save you a couple of steps. And this is important because as we get to more complicated quadratics that we're trying to factor, part of the process is always doing the following, which is multiplying the insides together, the I of the FOIL and the O of the FOIL. I don't really need to check this term. I know it's correct. The way, it's not that hard to separate x squared into x times x. I don't need to check to make sure that's correct. I did this thing by taking factors of 27. The only term I really need to check is that middle term. Is it minus 6x? Well, I don't need to do the whole FOIL. I just need to do the I and the O. Well, the insides multiply to minus 9x. The outsides multiply to plus 3x. Combine those by adding them together. You get minus 6x. We did it right. In other words, I can check my answer without FOILing the entire thing back together again, by just checking the inside and the outside. Okay? That becomes much more important as we get more complicated ones. which we won't do today because we're just about out of time. But let's do one more of these. Step 2.
Step 2 is determine the signs.
What are they?
A negative
and
a negative.
No, that would give me a plus when I multiply everything back together. That would give me a plus number. In other words, no matter what numbers I put here, notice that that is not going to FOIL back together again to give me a negative 12. It's going to give me a positive 12.
Yes.
So when I'm doing the process in reverse, when I see that negative sign, I know these have to be opposite. One has to be negative, one has to be positive. That's step 2. Step 3. Verbalize it.
What subtracts to make x but multiplies to make 12?
Okay, almost correct. It's not subtracts to make x, but subtracts to the number 1, because that's the coefficient in front of the x. In other words, there's a 1 right there. It's just not written. So what we need is factors of 12 that subtract to the number 1. What are those?
3 and 4.
So we know that there's 3 and 4 are two numbers. And finally, step 4.
Figuring out which one goes in which. And you said earlier that the larger factor goes with the sign of the middle term.
So what goes here?
4 goes first. And then
now, to check it, do my double smiley face.
Yeah.
It's minus 4x plus 3x. Add them together, you get minus x. That's correct middle term. We did it right.
We did do it right.
Now,
I wrote it all down.
Okay, well, good. These aren't that hard. These are fairly straightforward because you have a bunch of rules that you can write down and always use. There's no trial and error in any of these low degree of difficulties. It is worth noticing how you factor numbers. How do I factor 80? How do I find all the factors of 80?
Start with 1 and 80, then 2, which is 2 times 40, then 3, which doesn't work.
Well, let me give you my little secret on doing this. I cut this in half and double that as long as I can. Okay, well, I can still cut 40 in half. That's 20. Doubling 2 gives 4. I can do it again. 10 and 8. I can do it again. 5 and 16. I can't do it anymore. I can't cut 5 in half. Okay, so for numbers like this that you can cut in half each time, it's pretty easy to come up with all the factors. If you take a number like 27 and you want to find all the factors of 27, well, I can't even cut 27 in half. So the next thing I go for is to see if I can cut it in a third. And I can. That becomes 9. Well, because I cut it in a third, I got to multiply this by 3. Those are 2 more factors. Can I do it again? Yeah, I can cut this in a third to 3, multiply that by 3. Well, that's the same 2 factors. I haven't found any new factors, and in fact, that's all the factors there are for 27. That's the way I factor big numbers or numbers that it's difficult to factor. If I said factor 200, I would do it exactly the way I described. I would keep dividing this in half until I could no longer do it. If I could then divide it in a third, In other words, take the number 50. Okay, well, I can cut that in half and double that. I can't cut that in half anymore. I can't cut it in a third. I can't cut it in a fourth. But I can cut it in a fifth, which means I got to multiply this by 5. There's my other factors. So that's the way I find factors of numbers, which you have to do a lot of when you're factoring quadratics. So,
I wrote that down too. That's a great trick.
Yeah, it is pretty cool. All right, that's a good place to stop. I've recorded this. Takes my computer a whole night to process all my files. And so it won't be till tomorrow morning that I can actually send you a link as to where you can see this file. And that's the way it always is, and maybe something good to keep in mind, because a lot of students like to schedule their tutoring sessions the day before the test.
Yep.
But you can see that you'd want to do it 2 days before the test. Because you're going to want to have the session, and you're going to want to be able to review it before the test. So that's the only reason I let you know that now, is that you won't be able to see a recording of the tutoring session until 1 day after the session. Usually the next morning. But by then you're off to school. So
yeah,
during the school year. So we'll call it a session for today, and you've got another one same time on Thursday. Now, on Thursday, I won't call you. I will just text you the meeting ID number. Now, if you look at your desktop right now, if you can minimize everything and look at your desktop, you should see a GoToMeeting icon. It looks like this, like a flower, an orange flower.
Yes.
On Thursday, all you got to do is double click that. You don't have to go back to the website and re-download anything. If you double click that icon, the first question it asks for is the meeting ID number. I've already texted it to you. Put it in. We're going to be in a meeting. You don't have to change the audio setting. It'll stay on mic and speakers and everything.
All right.
Okay? So I will talk to you Thursday at 2.
All right. See you Thursday at 2 then.
Okay, Emily. Bye-bye.
Bye-bye.